good day. Today I will be present my analysis for interim 1 covering a dataset of 2000 that Sir Ken given to us. The goal of this study was to move from raw data to fully validated statistical model, testing for normality and comparing various probability distribution. I will walk you through the 8 key stages of this analysis, which is Excel minor versus computation, histogram, normality, normal curve, discrete, joint, continuous, and sampling, explaining exactly how each value was computed. So first I began by establishing our descriptive statics. To ensure accuracy, I perform a double check. On the computation side, I use a manual Excel formulas, which is this, and for the median, we have 314, for the mean is 311.017, and the standard deviation is 109.2173609 for the sample standard deviation. On the Excel Miner, I use the data tool pack to generate a descriptive report for all 2,000 rows. Comparing the two columns, our mean is, like what I said earlier, 311.017, and the standard deviation is 109.21. Because the manual formulas and the software result match exactly, we have a clean foundation. This step is the engineering equivalent of calibrating your instrument before taking measurement. So you can see the comparison, they are almost the same. So I think we go to the histogram. So we have the data, and before I do the solution computation, I do some sorted distribution. I use Sturgis rule, which is k equals to 1 plus 3.322 log times the class size, which is 2000. To determine that 12 classes were needed, I then calculated the range, which is this 375. I deduct the minimum from the max, so I get the 375 and divided it by 12 to get the class width equivalent of 31. Using the frequency array formula, I counted how many data points fell into each interval. So if you can take a look at this, we have the class number, lower value, upper value, frequency, cumulative frequency, percent frequency, and cumulative percent frequency. So how I get the frequency, I just put the lower value and then pick the lower value, which is 120, and then plus the class width, which is 31, and then I press the F4 and then minus 1, so I get the 150 and so on. So the total frequency is 1974, and the percent frequency that I get is almost exactly 100%, and the cumulative percent frequency is the same, 100%. And this is the histogram. The histogram visualizes the distribution by looking at the cumulative frequency, percent frequency. You can see that the data isn't clustered at one extreme but follows a visible peak, which gives us our first hint of a normal distribution. So how I get the histogram, I just select the midpoint and the frequency and then insert a table, and then that's it. I get the histogram. So this is the graph of histogram. We have the midpoint and the midpoint for x axis and the frequency for the y axis. So yeah, so next is normality. So here's the data, and again I sorted it, the 2000 values that Sir Ken given to us, and then I assigned a rank to each and calculated the cumulative probability of PZ using the formula P is equal to rank minus 0.5 over Z. And next I calculated the Z square for every point, and the formula of this is Z is equal to X minus ng mean over the standard deviation. And then this is the graph or normality graph. So I get the, I think it is in 315 or 10 something to 490 going up. So how I get this is I pick the sorted and then the z-score, and then insert graph, and then that's it. That's how I get the graph. So we look at the skewness, which result in negative 0.3 since this is nearly 0, the data is almost perfect symmetrically, and the mathematical proof allows us to proceed with confidence that the data follows a bell curve. So yeah, that's it. That's the normality. And then for the normal curve, I use the probability of density function, which is the PDF formula in Excel. The formula of this is norm this, I mean equal norm this times x, and then mean, and then standard deviation, and then false, and then close parenthesis. False argument ensures we get the exact height of the curve at the specific value. To make the graph readable, I created curve points by calling the scaling PDF against our frequency density. The resulting plot shows the theoretical bell curve perfectly overlaying our actual data. This acts as our model. If we were to pick a random number from this system, the curve tells us the probability of where the number will land. So first I get the descriptive statics so that I can solve the PDF and curve points. So after that, I do the graph by selecting the selecting the sorted data, then the outcome of curve points. So that's how I get the normal curve graph of this. So we can go to the next stages, which is the discrete. So in discrete, I tested 3 models, which are normal, binomial, and Poisson. For the Poisson distribution, I use the formula of P is equal to Poisson that this open parenthesis, and then the item or the data, the raw data, and then after that I select the mean. First is I get the before I solve that, I get the item, mean, standard deviation, and probability. So for the probabilities, I can give us a 0.5 probability, and then so how I solved it. You can look at this. This means that the probability is 0.5, and I press the F4 so that it will have a good answer. So after that, I calculated the this probability of binomial, and then probability normal. Then after that, after I calculated that, I moved to the cumulative normal, cumulative binomial, and cumulative Poisson. So for the cumulative, you will just sum the probability normal is equal to cumulative normal, and then probability binomial is equal to cumulative binomial, and then cumulative Poisson is equal to probability Poisson. So after that, we calculated the expected value for each model by multiplying the probability of each item by total count of 2000 data. So after that, I just, by comparing the expected value, we can see which model best predicts the frequency of specific outcomes. This is essential for quality control. Predicting low many items, we fall into a specific category. So this is the outcome graph. So for the probability normal, this is the graph, and then probability binomial, probability Poisson, and then this is the probability graph distribution. We merge these 3 graphs into one, so this is the result, and it will have a legends here. So next is the cumulative normal graph, and then cumulative binomial graph, cumulative Poisson graph, I just misspelled that, and then the cumulative distribution graph. So we can move to the next. So in joint, we have the data isolated 2 sets, the first 100 data points and the last 100 data points that sir can't give it to us. We calculated their individual probability and then their intersection. We have the first 100 data here, and I sorted it, and then last 100 data and sorted again, and then this is how I do this graph. So this sheet answer the question, are the data points related to each other based on when they were collected? Since the joint probability show independence, we know our 2000 observations are unbiased and not influenced by time in order. So it is equal to 100, so I think it is correct. And then in the downside, it is equal to 1, and I think that this is correct also. So let's move to the continuous. So in continuous, we have the data and the sorted, and I sorted it again. So I model the data using exponential, uniform, and triangular. So for the exponential, also we have a normal, density normal. For the exponential model, I calculated the by 1 over mean. For the triangular model, I use the mean and max and mode to define the peak. So continuous model are used when the values can be any decimal like weight or time. The triangular model is especially useful here because it counts for our most frequent value, which is mode, while acknowledging the absolute limit for the system. So this is the excuse me. So this is the density normal, density exponential, density uniform. Then after that, we have the density triangular, and then cumulative normal, cumulative exponential, cumulative uniform, cumulative triangular. And again, I do the descriptive statics, I mean, and then this is the graph of density normal, of the density and cumulative. We have the comparison of this graph. We have in the normal, we have something like this, and then cumulative is something like that. Density exponential, cumulative exponential, density uniform, cumulative uniform, and then density triangular, cumulative triangular, and then this is the distribution of density and cumulative graph. So for our last is sampling. So we have the data, and then I took random sample of sir can given us to have 1,000, 750, 500, 250, 150. So first is I get the normalized random number, and then I copy and paste as value, and then rounded it up, and then after that I used to do the n is equal to 1,000, n is equal to 750, n is equal to 500, n is equal to 250, n is equal to 100, and n is equal to 50. So I get the normalized random, and the mean of this is 308, standard deviation 107.034, variance is 11,456. So for the sample that sir can get into us, which is 1,000, mean is 303, standard deviation is 109, variance is 11,964, and so on, until it reached in sample n is equal to 50. So this demonstrates that the central limit theorem, you can see that as n gets smaller, the standard error gets larger, while the mean of 1,000 samples is very close to our population mean of 311. The sample of 50 is much more volatile. This proved that a large sample size is critical for engineering precision. So in summary, this interim took 2,000 raw data points through a rigorous statistical. We verified the data, proved its normality, modeled it across 7 different distributions, 8, and analyzed the impact of sampling. The result show a highly stable, normally distributed data set suitable for predictive modeling. So that's it. Thank you guys.